The topic of this video is to investigate tidal power as a sustainable energy alternative for remote communities based on Haida Gwaii. Haida Gwaii is also known as Queen Charlotte Islands, is a beautiful remote island archipelago off the northwest coast of British Columbia, Canada. The population is approximately 4,700 people and is divided between two main islands with a north and south grid. The south grid has a small hydro system. The archipelago is not connected to the main grid and derives the majority of their power from diesel generators. This is in conflict with the beliefs and ideals of natural stewardship and conservation held by Canada. We will focus on the north grid. The north grid currently uses 6 diesel generators with a combined capacity of 12.5 megawatts. They burn 10 million liters of diesel to generate 30 gigawatt hours of electricity per year. The largest peak demand can be seen to be about 6 megawatts for the old town of Mech. Depending on the load capacity, diesel generators produce approximately 0.778 kilograms of CO2 per kilowatt hour and about 2.5 to 3.5 kilograms of greenhouse gas emissions per liter of fuel. This amounts to approximately 26.8 megatons of greenhouse gas emissions per year. Why do we use diesel generators? Well, they are cheap and reliable and they provide a steady source of power. So what can be done? Is it economically viable to reduce fossil fuel dependency? Let's take a look at tidal energy. Energy from tides is generated from the gravitational pull of the moon, sun, and earth system. Advantages of a tidal power is that it is very predictable, clean, and sustainable. Haida Gwaii is well situated. Large tidal ranges and strong currents can be found along the coast of British Columbia. Two common methods explored are tidal stream turbines and tidal barrages. Tidal stream turbines rely on kinetic energy fluid flow similar to wind turbines. Tidal barrage works in a similar way to a traditional hydroelectric dam. A wall is built to enclose a bay or lagoon. Turbines placed into the wall run while the tide either runs in or out. When looking at the requirements of Haida Gwaii, tidal stream technology seems to be the better fit. A tidal barrage would not be suitable for many reasons, including the fact that the tidal range near Old Mech is just not enough. According to Energy BC, tidal ranges of about 7 meters are required in order for a tidal barrage system to be viable. An average tidal range of between 2 and 5 meters is observed from looking at tide tables. Also, the negative impact of controlling the tidal flow in the inlet wall with sluice gates is a big drawback for a pristine natural environment. Marine traffic would also be negatively impacted. In a research paper by Blanchfield, it was found that there was an expected maximum fluid flow velocity of 2.5 meters a second in Masset Sound. This is suitable for tidal stream technology. A simplified equation may be used to determine an approximate amount of power available to be generated by a turbine. There is also a value called the best limit, which states that the maximum amount of energy that may be produced from a kinetic fluid stream can be no more than 59%. In reality, this value is a lot lower, and usually closer to 30%. The average depth of Masset Sound channel is low. Tide is about 14 meters, and the narrowest point is approximately 700 meters wide. With the assumption of 9-meter diameter turbines, an array of 70 may fit across the narrowest section. Using the above formula, each turbine would be able to produce about 178 kilowatts of power. Using an array of 70 turbines generates 12.5 megawatts of power, but after applying the best limit, this translates to 3.75 megawatts of power. More turbines could potentially be deployed, but let's look into the levelized cost to get an idea of how tidal compares to diesel generation. The capacity factor is low for tidal energy as tides do not offer continuous flow. Capacity factor of 0.25 will be used. This is an average value taken from various tidal generation sites from around the world such as Wales, Scotland, and France. Making the assumption on cost and maintenance, annualized cost of $84,000 per turbine is found. This translates to an equivalent annual cost of about $5.88 million for the entire array. The LOCE stands for levelized cost of electricity and is found by taking the equivalent annual cost and dividing it by the estimated output. This generates an estimated output of about 9,855 megawatts per year, and the LOCE for tidal works out to be about 60 cents per kilowatt hour. For current diesel generators, using common values found for operational and maintenance costs, as well as using given fuel costs, the LOCE was found to be about 6 cents per kilowatt hour. This lower cost difference highlights the considerable financial hurdle that tidal power has to overcome before it can be considered financially viable. Ecologically, tidal power is a great choice, with unlimited free fuel. As tidal power is a clean, renewable resource, further advances in technology and learning are expected to greatly reduce the costs over the coming years. Carbon tax would also help create an incentive to move away from fossil fuels. In conclusion, tidal power is currently an expensive option, but with the environment taken into account, the advantages of clean, sustainable energy make this an interesting resource worth advancing.